And we're going to talk about forces and motion and the new stuff that we need to for Chapter 6. Going back to some very basic definitions that you should have had in physical science way back in the day, but we'll just take them one at a time. First of all, a force is just a push or a pull. Okay, forces can come in like a contact force where you actually shove into somebody, or it can come as a non-contact force where you have something like a magnet that's pulling or pushing, but it's just some kind of a pull or a push. Electricity can cause a pull or a push. All kinds of different things can be forces, but they have to be caused by something. Okay. When we talk about forces, there's something that's being pushed, and that we call a system. Okay, so the system is being pushed or acted upon by the force. So, we can identify what it is being acted on, and then what is doing the pushing, or where the pushing is coming from, even if we aren't actually using that specific thing. The environment is the world around the system. Okay, you know the word environment just from living life, but the environment is not necessarily just the plants and the animals and things like that. Environment is just the world around the system that's being acted on by a pull or a push. I said a second ago it can have something to do with actual physical contact, where one thing is touching something else. Okay, if you pitch a baseball and it comes and you hit the baseball with the bat, then you have a contact force, and that's what caused the baseball to go, because it got hit by the bat. And so you've got contact by touching. A contact force can act over a certain amount of time too. You can be pushing, let's hope not, but if your car breaks down and you're pushing it down the road, you could have that contact force for quite a while if you're pushing it for a while. Okay. And then a long-range force, this is the specific thing where you're not having contact, but it's still acting, it's still causing a change, it's still a force like gravity or a magnet. And later on down the year, we're going to do a special activity that has to do with gravity that shows basically how it works in the context of how Einstein conceived it, how he believes how he believed that it had worked. And then the agent is the thing that's doing the pushing or pulling, the thing that is causing this force to be exerted. Okay. Now on your paper you have this great little drawing to start with. I do have to say this section I did drawings a little bit better than I've done in the past drawings, but the last drawings are terrible, so the new drawings being better, not really for applause, just that I took my time a little bit more. Okay, so we've got a book. Usually when you're drawing a pictorial model showing what's happening and the forces that are acting in the situation, the actual thing that is having the force exerted on it is usually encircled with like a dashed line. So you draw your basic thing, and then this actually shows all the forces that are acting. Notice that the force in one direction exactly balances the force in the other direction. The book is just sitting here on the table. We know that gravity is acting on the book. Okay. Gravity comes from the Earth's mass. Even though it's not a contact force, it comes from the idea that the Earth has mass. So therefore, anything that has mass is actually pulling on every other thing. Okay? But because the Earth is so big, it exerts a bigger force than just your random little thing that's sitting near you. So you've got this giant force that's pulling on this book, okay, because the Earth is so massive. So it's the force of the Earth's mass on the book. But if that were the only thing that were acting, it would just pull it down, and it would just go towards the thing with nothing to stop it. So in order for this book to be still on the table, there has to be an equal and opposite force. And that's the force of the desk on the book, if the book is sitting on a desk. So you've got, when you're trying to figure out how these forces go, you have to figure out what is acting. Usually, in most cases, gravity will be one of the forces that you take into account. But then there's these companion forces that you can't forget about when you do these, whether it's a force of friction or whether it's whatever kind of force it is that goes along with. So it's not usually just one force acting. There's usually several, although there can be just one. All right. So what we want to do is we want to draw a model for a sled being pulled sideways at constant speed. Okay? So you need to draw yourself a sled. Okay? And we don't necessarily need to draw the agent of force, but you need to draw the sled itself. And you need to also just kind of put a little rope on it to show that it's being pulled. So he's got a little hat, but that's not part of it. But this is a sled. This is the system. It's encircled by a little dashed line. This rope just kind of shows that he's being pulled this way at constant speed. And then we need to analyze what the forces are that are on this guy. All right, you don't have to put a guy on it. You can just make some kind of a rough drawing of that. Something's funny. Okay, all right. So when we're thinking about the forces that are on this particular sled, okay, what is one thing that we know is acting on this sled? Yep. Gravity, sure. Gravity, the force of the Earth's mass on the sled. And that, which direction would that be? Down. Okay? We're not even talking positive or negative here. We're talking just up or down. So it's down. So the fact that this sled is not plummeting down through the earth means that there has to be an equal and opposite up force. Okay, and that up force that goes with the down force is the force of the ground on the sled. But we have other things. It says that it's being pulled sideways at a constant speed. Okay? So since it's being pulled sideways at a constant speed, you can imagine that there's a sideways force being pulled on this to the right, just because of the way I have it drawn. But it says constant speed. Okay? Now, in order for there to be constant speed, the left force and the right force also have to be balanced. Because when you balance those forces and you have a left that matches a right, you have a zero force, which translates to a zero acceleration. So our force diagram for this, you've got the force of the Earth's mass on the sled that pulls downward, and the force of the ground that pushes upward. They're equal and opposite. This up and down one are the ones that keep it from flying off the earth, and then also keep it from plummeting down through the earth also. But the fact that it's going at constant speed means that the other ones also have to be equal and opposite. So the person pulling on the sled got it going, and they are pulling this way. But what comes against, and I don't know if you can see it from where you're at, but you've heard of friction, right?
Yes. Yeah.
So friction is what's going against when you're pulling that sled sideways. So you've got the force of friction pulling sideways, and you pulling with the rope. And yes, friction does do heat like you were just demonstrating. And as we go through this chapter, we'll talk about how we can measure friction and how we can determine how much friction based on surfaces and those kinds of things. But for right now, we just need to be able to identify all the forces. Okay, this, when you're doing the problems on this, making a diagram that shows all the forces is not optional, because you're going to need that diagram to help you to figure out which way acceleration is sometimes, figure out how much force is, because knowing the idea that you've got equal and opposite helps you with the numbers. Because if you don't have the information to figure out this piece, but you have the information to figure out this piece, once you have the number to the right, you have the number to the left. So drawing this out really helps you in those ways. Okay. Now that drawing that we talk about where you have the forces all showing is called a free body diagram. Okay. When the system's represented by a dot and all the forces are shown, it's a free body diagram. And yes, that is on your sheet. And yes, there are some free body diagrams on here, but I want to talk about what things represent. So you've got this one. Force of gravity, so good call. Force of gravity, or the force of the Earth's mass on whatever it is. But this is the downward one. It's a force of gravity pulling down. And so there's nothing else acting. Just the force of gravity. A little bit of a false situation, because usually there's at least a little bit of air that it's going through but this is just purely gravity only acting on whatever it is. And so this would be the case where you're not considering the air and you just drop something, force of gravity. Okay, and that was happening on your last test where we had force of gravity acting on various things. What would be happening in this scenario? Yep. Okay, I'm not going for subscripts this time. I'm just saying there's a force A pulling this way and a force B pulling this way. But, yep.
I'm going that way. That's friction?
Maybe.
And the one going this way, that's, I guess that's acceleration. Yeah, it's a force, right?
It's a force. Yeah, they're both forces. We don't know what the forces are, quite honestly. But we know that they're equaled out. Okay, so there's two possible things that might be happening here. Okay, this, whatever the object is, might be at rest, but it might be also moving at constant speed. We don't know which direction it would be moving at constant speed because we don't know what which one was pulling first. But they are equaled out, so this particular scenario means it's going to be either at rest or it's at constant speed. Yes?
So you're saying if I'm not moving, that means that something is pulling me that way and something that way?
Not necessarily left and right, but definitely up and down. Because there's definitely what's pulling you down. Gravity. Gravity's pulling you down, and what's pushing you up right now is the seat of your chair. Okay. And right, so well, and the part of your feet, sure, your feet are on the carpet, so part of the carpet is pushing you up. And if the chair was weak for whatever reason, then you would fall off the chair. And that would be bad. Yeah. But then gravity would win for a while until you hit the floor, in which case everything would equal out again, and then you'd be at rest and the up force would match the down force. On this one, this was interesting. Let's talk about not necessarily what's causing those forces, but we've got four forces that are pulling on the same thing. So since we've got four forces that are pulling on the same thing, what's going on with this object? Which way is... Yeah. It's going down in this picture, sure. Yep. Possibly sledding down a hill, sure. Go ahead. What do you think?
I was gonna say like it went past, like you know when it's going down, but it goes past the x-axis.
Maybe goes past the x-axis, but we don't have. There's nothing that says anything about position or where something is on this picture. This is simply the forces. What this is really saying to us is that the right and the left force, they're canceling each other out. Okay. But the force that's going this way and the force that's going this way, they're opposite of each other, but they're not equal. That means that this downward force is winning. And this downward force winning, the amount it's winning by is what we call the net force. Okay? So what we can do then is once you have these drawings, you can talk about the force that's the combination of all the forces acting on this particular object, which is represented by a dot. So the net force is the vector sum. We've used that word vector sum before a couple chapters ago. Vector sum of all the forces that are acting on the system. So what we can do is we can talk about the net force for each one of these particular scenarios. So this one actually, even though it has the most parts, might be the easiest. So which way is the net force on this one? Yeah. Downward, sure. Because these two cancel each other out. The up is this much, the down is this much. So this downward force is winning by just this little amount right here. And so your net force looks just like that. What you can do if you want is you can draw this on this side, or you can draw this on the other side. Oops, I can't move it right there very conveniently. Yeah, I can move it like this if we need to move that over. So your net force is pulling downward. I know some of you might want this, so let me copy and move that over. There we go. So here's our net force. Notice that I have the subscript net on it, N-E-T. Do not use the subscript N, because the subscript N is its own thing. N stands for the normal force, not the net force, and that's a whole different type of force when we start analyzing them. But here's your net force. The net force is the total when you put everything together. So this is a vector. It's down. It's exactly as much further. It's how much this is winning by. So what about this one? What do you think about the net force on this?
There's no net force.
There's no net force. So how do we represent that as a vector? A dot, yes. So our F net here is a dot. F net here is downward because this is the one that's winning. F net here is a dot because left, right, they cancel each other out. Then right here, it's just downward, and it matches. It's exactly a match because all of the force that's being exerted goes into the net force. The total is, there's only one thing to add, so there's nothing, it's just that number. So our net force is the vector sum of all the forces acting on the system. If there's only one force, there's nothing against it, and then otherwise you've got the up versus the down, like that. Okay. All right. Everybody still with me? Okay. Great. And that brings us to what's known as Newton's second law. And yes, we're looking at the second law before we look at the first law. I know that sounds weird, but Newton's second law before we look at the first law. Acceleration is directly related to the net force. Okay. F net equals ma is the equation that got me all the way through my physics in college. I had to use this over and over and over again, but F equals ma. The original way to write this, though, is acceleration equals the net force divided by the mass. So it depends on two things. It depends on how much the net force is and how much the mass is. So the higher the mass, if you have the same amount of net force, but you have a higher mass, then your acceleration isn't going to be as great. So that should make sense because you've had a bigger, heavier object and the same amount of force, then your acceleration, it would have to be less acceleration. Not as much change in velocity could happen. But if you have a smaller mass, then that means that more of that force goes into changing how fast it's going and relates to your acceleration like that. Okay, make sure that that's there. Yeah, it is. So first off that we can observe, I want you to write this down. If net force is 0, what would be the acceleration then? 0, okay? Because you could plug that number right in. So if the net force is 0, the acceleration is 0, please write that down. And then be prepared to study it come test time. Yes. Yay, finished. Okay. Thank you. Thank you. It's going to be good. I have faith. All right. We have more observations to talk about. Second observation, you need to write down observation 2. I didn't put this on here for you. So if acceleration is 0, how much is the net force?
0.
Also 0. So they go hand in hand like this. Notice this says 0. Force is measured in newtons, which we haven't talked about yet, but this N stands for newtons. And so 0 newtons, not on. This is 0 newtons. 0 meters per second squared for our acceleration. So that. So here's a really, really important thing to get your head around. That no net force always means no acceleration. Okay? No net force, 0 net force always means no acceleration. And net force and acceleration will always be in the same direction if it's a non-zero number. Okay, so super, super important. Those diagrams, those free body diagrams that I was having us take a look at are super important. Comes to determining what is going on with these forces, which helps determine what's going on with the acceleration, which we're going to need to go back to the stuff we just did in this chapter with those problems and apply it with the net force and the forces and the acceleration and those things. So super, super important that we get into our head that the net force and the acceleration will always be in the same direction. So I'll give you a chance to jot that down real quick. And I think just to make sure that you know make sure that we're on the right place and that you're understanding what I'm talking about, I will need for you to do a couple problems, or actually to do a problem right now. I'm going to pause this and you're going to do something in your book because I need to make sure you're with me. Okay. Where is it? Oh, there it is.